Moving on to the properties of rational numbers. We have already worked out with the rational numbers few operations and few basic facts we have learned and illustrated also with examples. So it is now the time where we identify and list out certain properties of the rational numbers. Now, we have already learned the basics of algebra, and we know that we can generally say certain properties, formulae, etc., so that we can use it wherever relevant. So for any three rational numbers, capital A, capital B and capital C. But this capital A involves again numerator and denominator, as we are considering rational numbers here. Maybe it is A by B. It can be a fraction, we know, negative fraction or positive fraction depending on the situation. And under the considered operation star, because we have four basic operations, generally we write star, though it is used for multiplication. Let us use the star for general form. The closure property, let us write. It says if A star B, that is the operation between the two rational numbers, when done, if the answer, the resulting answer, that is result of A star B, is it there as a member of the group? In the sense, does it belong to the group or belong to the set? If it belongs, we consider the set as closed. In the sense, the answer is there in the closed house or closed set of the numbers, whichever we consider. Here we are considering rational numbers. So moving on to commutative property, we consider any two rational numbers randomly chosen from the set, that is A star B, under the operation considered, in the sense if it is plus A plus B or if it is into A into B, likewise. So A plus B or A star B should be equal to B star A. Then we say that the commutative property holds good. Commute refers to move, to and from. So in the dictionary, if you look for this word meaning, commute. So it should be this way, from going to and coming back. So it should be true both the ways. It is important. Next, associative property, associate. So we are associated with our school, we are associated with our home. So it is associate, connected to or make a group. So I am going to group. So associative property says when three members of the group or three numbers, rational numbers, are grouped, first grouping the two and then combining it to the third, and in another possible way, combining the second and the third grouping and then combining it to first one, does not alter the result. It should be equal. So grouping any two and the other two, whichever combination, it should be true. So if you just observe, associative property contains commutative property in it, or it is the result. If commutative property is not true, normally associative property also is not going to be true, because it is extended part. So always whenever we use both the properties simultaneously, we should think where which one is used. So let us move on to a pictorial representation and consider the same properties in a different way. You can see two circles. The inner circle has integers in it. Consider it as a family of integers, and the outer circle has rational numbers in it. But the outer circle has integer circle in it already inside. So exactly the relation between integers and rational numbers is depicted as one is contained in the other one, because all the integers are rational numbers also, because they can be written as by 1. Say 5, 5 by 1, 10, 10 by 1, 0, 0 by anything. So likewise it goes. So the three properties we have taken here. The closure property, commutative and associative. Already discussed the basic forms. So let us consider the operations. A, the orange, as addition, subtraction, multiplication and division in the same order in the clockwise direction. Closure property, let us see how it pictorially holds true. And commutative also, addition, subtraction, multiplication, division in the clockwise order. And next comes associative. So consider a magical box of operation of addition enters the set of integers. We have already studied what happens there. Say that magical box is placed in the integer circle and all the integers, you can imagine they are the Lilliputs, and any two of those enter that magical box. What happens? They undergo that operation and they transform into a different number. And if that transformed new number, if it is found in the integer circle, then we say the closure property is true. It should be there. I am there. It should say hi. So I am there. The answer is there. After transforming also, when they come out of the box, it should be there. The same answer should be there in the integer group. So it is very nice to imagine this way. So for addition, what do you think? For integers, we have studied in 7th standard that it is, yes, you choose any two integers and those two Lilliputs jumping into the box and they undergo the operation of addition, they will be coming back and they will be seeing the answer in the integer group. But for subtraction also, you imagine, because there are negative numbers, it's not like whole numbers now, they are negative numbers are there, therefore the answer is also belonging to the same group. So they are happy to see and say hi. So then multiplication also, the multiplication magical box, if two Lilliputs, the integers jump into that and the answer is also one integer only. But the division is not going to be so. When two integers jump into the division magical box, what they get transformed into, it's like a fraction. So they won't find the answer in the integer circle. They are unhappy or maybe they are sad to see. So it is, we say that the closure property for integers doesn't hold, because the member, the resulting member is not found in the group of integers. So similarly, I am not going to extend the thoughts or this concept into integers area. If you see the commutative property, you can consider like this. The same Lilliput picturization, you can consider like this. See two integers, and when we consider two integers for commutative property, say I will Lilliput A and Lilliput B. First Lilliput A enters the magical box of addition and Lilliput B enters later, and immediately they get transformed into a new integer. In that case, what they get transformed into is a resulting number. If it is not so, Lilliput 2 enters first and then Lilliput first one, the A, whatever we named, it enters first, but the resulting integer or the new transformed Lilliput is same, then we say it is commutative property is true for addition, and we have found that it is true. Already it is learnt in grade 7. So when it comes to subtraction, it is not so. Say Lilliput A is 4. It jumps to the magical box of subtraction, and next comes 5 and 4 minus 5 is done. And we get -1, and the opposite is done. It is not -1. It is another number. So the sign is different means it is not same. Therefore, for subtraction, a minus b is not equal to b minus a, the general form which was shown in the previous slide. Or two Lilliputians cannot jump in any order when we consider the magical box of subtraction. They will get a different answer. So here it is not spotting only the answer, it is answer also should be same. It is not like closure. In closure we just spot. They become very happy if the answer is there. Here it is not like that. In whichever order if they enter, the answer should be same. It is not answer is there. It is answer should be same. So subtraction is not going to be true. So likewise for multiplication it will be true, and for division it won't be true, because 2 by 3 is not 3 by 2. This is already taught to you. So when we have discussed, moving on to associative property, we have already studied that commutative property is a building block for associative, and they are connected. So if commutative property is not going to be true, there is least possibility that associative property is true. So accordingly, here we take three integers, Lilliput A, Lilliput B, Lilliput C. So you can imagine like this, Lilliput A and B togetherly jump and they form a group. They already get transformed. And now Lilliput C joins. Me too. So it will enter, and then the newly transformed form of Lilliput A and B then getting combined to Lilliput C, and then how it is like, it will be one new form. And then if it is combination of different ways, like A and B first and then C, or B and C first and then A, so there is no difference, it is same. So this is called grouping, and it is associative property. We are going to check for rational numbers also, and as we have already studied rational number operations, it is very easy to visualize this. So when we come to check for closure property of rational numbers, just check any two rational numbers when added. We have already added, taken LCM and added. Always we got rational number as answer. So we spotted the answer there. Therefore it is yes, closure property. Subtraction also yes, because whether it is negative or positive, answer was rational number. Multiplication also yes. Division no. Can you tell me the reason? Why? Say I am considering 2 by 3 divided by 5 by 4 or whichever, I may get a rational number. But the very definition of rational number says denominator cannot be 0. In the sense, there can't be any number which divides by 0. So 0 is also a rational number, and any number divided by 0 is not defined. So we cannot consider the closure property as true. Next, coming to commutative property, already we have seen when we add two rational numbers, they can be added in any order. We take LCM of the denominators. It doesn't matter the first one is written next or whichever position. Even if there are three numbers, I can write third one as first one, second one as third one, etc. No problem. So addition is also commutative, and subtraction, of course, no. Why? Because as mentioned, for integers it is not true. Rational numbers also will not be true. Say a simple example of 1 minus 2, 2 minus 1, because 1 and 2 are also rational numbers. So whatever properties we have discovered true for integers holds true for rational numbers. We are going to verify it ourselves, and these properties are going to be used to solve sums in a quick manner. Already we have seen how to solve sums in a rapid manner so that we can be smart enough to deal with such problems. Try to recollect the integers closure law or closure property. Considering integers a and b for addition, one example is shown here. Minus 7 added to minus 3 is minus 10, an integer. Another 4 plus 3 is 7, an integer. 7 minus 3 is 4, an integer. Subtraction, yes. Another example for subtraction, 5 minus 10 is minus 5, an integer. And for multiplication also, minus 8, product of minus 8 with 5 is minus 40, an integer. But for division, 5 by 8, both integers are taken, but the resulting is a rational number. So it is not an integer. So closure property is not true for integers. Commutative law for integers. 5 added to minus 3 is same as minus 3 added to 5, and it holds true. But not the same for subtraction. Simple number, positive numbers only depict that. The sign changes. Now the product of two integers can be taken in any order, therefore it is commutative, but the division is not allowing that, not commutative. Example is very clear. The associative property for integers, three integers are taken as examples. So minus 6 added to the sum of minus 4 and minus 3 is same as minus 6 added to minus 4 and that sum being added to minus 3. So it is shown clearly. When we verify, we don't open the bracket at a time on LHS and RHS. We have to prove that it is true. Like that Lilliput jumping together. So here minus 4 and minus 3 jumped together into the box and they became minus 7, and that new transformed Lilliput now combined with minus 6. That is one possible way. Second trial, what happened? Minus 6 and minus 4, these two Lilliputs jumped in and they became minus 10, and that was added to the third Lilliput minus 3 and the result was same. So you cannot show at a time, open the bracket, and this was taught to you last year how to verify. Separately within the bracket you have to calculate and then that answer should be shown and the resulting answer should be equal. Similarly, the third one, the multiplication of integers, how that associativity is holding true is shown. How two integers got multiplied and they got transformed into new number and that was multiplied. So 5 got multiplied to minus 2 and minus 3 product, that is 6. So 30 we got. Similarly, other possibility is 5 got multiplied to minus 2 and then it transformed into minus 10 and that got multiplied to minus 3 and then answer is 30. So both ways it is true. You should show both the ways. So that is true for rational numbers also here. You should be proving both LHS and RHS separately within the bracket, calculation, etc., whatever explanation, detailed step. Similarly, for division it is not true. That is also proved. You will get for LHS one answer, RHS another answer. Moving on to rational numbers now. We are now in grade 8 and rational numbers law. And all the rational number features, operation, everything is taught to you in grade 7. So this should be very easy to understand. Consider the general form addition. A plus B is a rational number. Let us check. Any two numbers taken, minus 5 by 12 added to minus 1 by 4. LCM taken when adding, not cancelling. So the resulting is a rational number, minus 2 by 3. Similarly, one more example for addition is shown. For subtraction also it is shown and the answer is minus 41 by 36, which is a rational number. Now for multiplication also, two rational numbers randomly taken as examples. When we multiply, we don't take LCM. minus 4, 6, minus 6 multiplied 24, 5 and 11 multiplied 55, rational number obtained. So fifth example, division. 2 by 5 divided by 5 by 3, you got 6 by 25, of course. When we divide, we take the reciprocal of the second one, that is 5 by 3 reciprocal 3 by 5 is written, and then the calculation is done. Note it. So it's a rational number. So why then it is not true for division? Consider the reason. 2 by 0. It is not that for few numbers only it is true. It should be true for all the numbers, not an exception. So here 2 by 0 not defined, not a rational number. 0 is a rational number, but 2 is a rational number, but dividing 2 by 0 not a rational number. So it is not going to be true. Commutative property. The commutative property for rational numbers is again very similar. When we add two rational numbers, we take the LCM of the denominators. So, is there any difference in the order in which it is added? Whichever the order is, answer will be same. It is shown there, 5 by 6 added to minus 4 by 9. LCM is 18. Accordingly, and then it is got 7 by 18, and now minus 4 by 9 added to 5 by 6. Which is written first is not a matter. Answer is same. But for subtraction, it is not so. You can observe there 2 by 3 minus 1 by 6 and 1 by 6 minus 2 by 3. Of course, this complication is not needed when it is not true for integers. All the integers are rational numbers. Take 2 and 3 are the two rational numbers. Say 2 and 3 are rational numbers. So 2 by 1 minus 3 by 1. 2 is 2 by 1, right? 2 by 1 minus 3 by 1 should be minus 1. And the other one should be, other way it is 1. So how can it be true? Multiplication you consider now. Third one, which is the multiplication of two rational numbers 3 by 4 and 5 by 7. Say example is given. When we cancel, even if I write 5 by 7 first and 3 by 4, it doesn't change. And multiplication of course is commutative for integers. So it should be also for rational numbers. So examples, you have to take several examples of your own and check. Practice makes us perfect. Several times you do it and verify. The concepts, they get churned and digestion happens there. Digestion of the knowledge. So for division, you can just verify minus 5 by 4 and 3 by 7. Two rational numbers taken. One divided by the other. When the order is changed, it is not same. Right? Yes. The associative property for rational numbers. General form is written in the top box shown for all the operations. Consider the addition. Three numbers are shown, minus 3 by 4, 5 by 6, minus 4 by 9. Okay, in this 5 by 6 and minus 4 by 9 are grouped. Second and the third one in the LHS. So what is the result of that? 5 by 6 and minus 4 by 9 being added in the bracket. 5 by 6 and minus 4 by 9. 18 is LCM. 6 3s are, 5 3s are. So 15 by 18 and minus 8 by 18 comes. So the result is 7 by 18. 7 by 18 added to this outside the bracket number minus 3 by 4 gives us minus 13 by 36. That is the LHS. Now consider the RHS. Minus 3 by 4 and 5 by 6 first added. That gives minus 4 by minus 9 by 12 is equivalent of minus 3 by 4 and 10 by 12 is equivalent of 5 by 6. So when these are added, you get 1 by 12 and that is being added to minus 4 by 9. Finally you reach at minus 13 by 36. It is same. So associative property of addition is very useful when we solve sums. We are having few examples where otherwise we don't take this property for calculations and simplification of sums. But if we take this, it is very easy, and already in the previous presentation it is shown how we combine the similar denominators. That is exactly what associative property is. It is not taking all the denominators LCM at a time. Instead we combine and make it very simple so that we can, certain calculations even can be done in mind. So move on to the next example. The same I mentioned, which was already illustrated in the previous presentation. Just observe the two. The left hand side has direct method, no using property. All the denominators 7, 11, 21, 22, all the four denominators LCM is 462 and equivalents are written. 3 by 7's equivalent is 198 by 462, minus 6 by 11's is minus 252 by 462. Today's first slide, all equivalents are written, higher order equivalents are written and then added, and you get the answer minus 125 by 462. But see the adjacent side, same sum, smarter calculation. 7 and 21 is denominator, because it is 21 itself is LCM of these two are combined, and minus 6 by 11 and 5 by 22 are combined because 11 and 22 have their LCM as 22. So when these are grouped to one particular step, 1 by 21 and minus 7 by 22, we got the answer. Till there we don't require that 462 LCM. It is very easy. So if you write 1 by 1 and you do it yourself, you will realize 1 by 21 plus minus 7 by 22 comes. Until there you are safe. Next, 22 minus 147, and that is however LCM part of that 462, and then correspondingly numerators are written. So answer is same, it doesn't change, but the method is simple. So when there is easier method and the property can be applied in a best manner, it is wise to use it. So it is important to note that we are using both the properties by using commutativity and associativity. First, when I write 7 and 21 together, I decide to combine these two, it is commutative property. As soon as I write the bracket, it is associative property because I am combining these two. It is something like how Lilliput's planned, okay, these two will jump to the box first. That is commutativity. They are similar. But when they formed, they jumped together and they transformed, it is associativity. One more example. See how the difference is. Like it is addition of rational numbers, 5 rational numbers given, and all these denominators have LCM 120. First regular method is shown. So 3 by 4 is equivalent to 90 by 120. Minus 3 by 5 is equivalent to minus 72 by 120. 2 by 3 correspondingly 80 by 120. It is large numbers and it is very not very easy to handle. This complexity is reduced by using the law. You can just see the right side where 4 and 8 are combined, the denominators 4 and 8, and 5, 3 and 15 are combined. Of course they have LCM 15. So when these three are combined, we don't get LCM 120 at all. And the denominator 15 part comes to minus 3 by 15, which can be again written as minus 1 by 5 in the simplest form. So only LCM is 8 and 5, LCM 40. So it is very easy, answer is 47 by 40. You have to convert to mixed however. So the application of the property is very clear, where it is Not because it is asked to use the property, it is applicable and it is helping us to do the calculations in a quicker manner. That is why we are using the properties wherever relevant. Of course, it is not going to help us only for the sake of checking whether the property can be used. Then we have to use for the sake of the question. Otherwise, always properties, if relevantly used, they make the calculations simpler and faster. Here one more example which is very relevant. So 5, 20 and 10 combined 20 LCM, 7 and 14 combined 14 LCM. But without the shortcut or without the use of property, it would have been lengthier. 140 would have been the denominator, and then correspondingly every numerator would have been bigger and chances of making errors more. Here at least we are safe till 60% of the sum. So we are using both commutativity and associativity again. The associative property for subtraction of rational numbers. Taking any three random rational numbers, say minus 2 by 3, minus 4 by 5 and 1 by 2. The first number A minus B minus C, where the second and the third are combined, grouped as LHS form, and in the RHS first and second are grouped and third one is outside the bracket, and each is simplified separately. Remember, it is important to simplify the brackets first. Until you get an answer for bracket, you cannot open the bracket. You cannot take LCM at a time for 3, 5 and 2, though you write LHS and RHS separately and do the same. So it is important that minus 2 by 3, the first number, and subtracted the second number, minus 4 by 5, minus 1 by 2. So this minus 4 by 5 and 1 by 2, when subtracted, the result is minus 13 by 10. At minus 8 and minus 5 subtracted and minus 13 by 10. So now this minus of minus, minus 2 by 3, minus of minus, that is one minus is the subtraction minus, another is the sign, resulting sign of the rational numbers subtraction. So it gets plus 13 and the answer is finally 19 by 30. This is already taught to you last year, how to subtract a rational number. But when we consider the bracket, remember the bracket should be simplified together. So minus 13 by 10 is a must. You should get the answer, then only you should go ahead. Now consider the RHS, minus 2 by 3 minus 4 by 5, which is minus of minus again plus minus 2 by 3 plus 4 by 5 comes, and you take the LCM of 3 and 5, that is 15, and you add it, minus 10 plus 12 comes as the resulting equivalence, and it is 2 by 15. So it is important that you obtain this. First within the bracket 2 by 15 comes, and then you do minus half. So that comes as minus 11 by 30, which is proving that we cannot use brackets in subtraction. That is, associativity is not going to be true for the process of subtraction of rational numbers. And it is already learnt that it is not going to be true for integers. Of course, it is not going to be true. So when you are asked to verify for 3 given numbers, this is the process. You have to take 3 numbers and put them in the A minus B minus C not equal to A minus B bracket minus C in that form, and then you have to simplify as shown. So it is better you write and learn. Taking any 3 random numbers, better you verify it and you become very stronger in the calculation of operations or in the calculation of difference, sum, of rational numbers and taking LCM accordingly. Considering the multiplication process to check for associative property. Now, three rational numbers are randomly taken, minus 5 by 4, minus 6 by 11 and 2 by 7. In the first LHS, minus 6 by 11 and 2 by 7 are combined within the bracket and the product is calculated within the bracket. Whatever is there, the resulting answer should be calculated and then the number outside should be multiplied. It is not that you open the bracket at a time as mentioned for addition variety. So here also you have to follow the same. Get the answer for minus 6 by 11 and 2 by 7 multiplied, minus 12 and 77. So that answer gets multiplied to minus 5 by 4 and the resulting answer is 15 by 77. Now consider the RHS. How to write RHS? First two multiplied, that is minus 5 by 4 and minus 6 by 11 multiplied. So here you have to calculate the resulting within the bracket, that is minus 5 and minus 6 is 30 multiplied and 4 and 11 44. But in case it is cancelled 4 and minus 6, it reduces and you get it as 15 by 22. And that gets multiplied to the third number 2 by 7 and the answer is 15 by 77 and both are same. LHS and RHS, it shows that the associative property is true for multiplication of rational numbers. And commutative is also true for rational numbers, hence associativity also true. But normally in multiplication we are using this property without our knowledge. We don't pay attention to that we are using it, but we are not using the brackets. We cancel out from any numerator to any denominator without thinking much that we have to combine that particular numerator, as we have seen in the first example. One of the example I showed, we don't combine like that and we cancel. And it is evidently used. It is already hidden in the procedure that we cancel as many rational numbers given, we cancel whichever combination best possible. That too repeated number of times. See this example. The example which I showed in the beginning for simplest forms, if intentionally I have to show where the property is used, it is like how it is shown here, use of commutativity and associativity, the printed form. It is minus 4 by 5 combined with 15 by 16. The reason is 5 and 15 can be cancelled and minus 4 gets cancelled with 16. So with this reason the two rational numbers are combined. So absolute example of associative property of multiplication. I have associated the two rational numbers minus 4 by 5 and 15 by 16. And 3 by 7 associated with minus 14 by 9. And all are multiplied. But I am multiplying first two as shown in the bracket and the next two as shown in the bracket. First two when multiplied, 5 and 15 get cancelled and 4 and 16 cancelled, we get minus 3 by 4. And similarly second bracket when simplified we get minus 2 by 3. 3 and 9 cancel, 7 and 14 cancel. So finally when multiplied again we get half, 1 by 2. The same we did that time when I showed simplest form. But when any sum is given for 4 rational numbers or 5 rational numbers multiplication, we cancel like that only, we don't use any of these methods. But this is how actually the property gets into our calculations without our knowledge and we are using it without our knowledge. But in addition it is very evidently shown, and we have shown in the past 3-4 examples, previous slides, very clearly that LCM becomes very big if you go for direct calculations. So there we have to follow the easier method of using these properties, keeping them always in our mind. Associative law for division, verification is shown here. It is not true, but when we verify, we have to prove that it is not true by once again the same process as we explained for subtraction. Three numbers, rational numbers are shown, 1 by 2, minus 1 by 3 and 2 by 5, and the first two are one divided by the other and third one is later taken. So in the LHS, first divided, later 2 by 5 taken, and in the RHS it is 1 by 2 taken out and then minus 1 by 3 and 2 by 5 combined within the bracket. But both the process as per the condition done, and then we get the answer different. One is minus 15 by 4 we get, another is minus 3 by 5 we get, and they are not same. That is why not equal is written. 1 by 2 divided by minus 1 by 3 done first, and that answer divided by 2 by 5 is not equal to 1 by 2 divided by the within the bracket minus 1 by 3 divided by 2 by 5. So you have to take this sum and do once again in your notebook. Then it will be very clear and the property is illustrated. The use of commutativity and associativity in a different type of sum. 4 rational numbers, 5 rational numbers are given, combination of operations, addition, subtraction. It is rearranged to combine denominators 3 and denominators 5. The ones which are having denominator 3 are combined, and the one which are having 5 are also combined, and minus 2 is done later. Actually, if you visualize these 4 by 3 and minus 2 by 3, it can be done in mind. 4 by 3 and minus 2 by 3, it is 2 by 3. So which is, of course, it is shown there after long method. It looks very lengthy, but it is very simple. And minus 4 by 5 and 7 by 5, if you observe the second one and the fourth one, 3 by 5 is the answer, because only the numerator minus 4 plus 7 is done, 3 by 5, and the same is there. And minus 2 is done at the last. So it is very easy. 3 and 5, 15 LCM once again. So associative law is shown, and how the answer is again a rational number. You will get it in the form of P by Q. To the right, writing the given decimals as rational numbers and representing in the lowest forms is shown. Some 3 examples are shown. Refer to it. Decimal expanded form, and then writing the fraction or rational form in simplest terms.